So for our kinematics unit, we're going to need to be really good at just two math things, the Pythagorean theorem and SOHCAHTOA. So the Pythagorean theorem you've seen before, we'll just quickly review it. It works when you have a right angle triangle and it's useful for finding the lengths of the sides. So the two sides near your right angle you can call A and B. The side opposite the right angle, that's the hypotenuse, that's going to be C. So the hypotenuse is C. Once you know that, you can just write down Pythagoras' theorem, which is that c squared, the hypotenuse squared, is a squared plus b squared. The proof to that theorem is really lovely. If you ask me, I would be happy to show you sometime. It's quite fun. In this case, just solving for c, which is just going to be the square root of a squared plus b squared. Notice that the square root does not cancel the squares because there's addition under that square root sign. Tossing your numbers, a squared is 6 squared, b squared is 8 squared, 6 squared is going to be 36, 8 squared is 64, add those together you get 100, and the square root of 100 is plus or minus 10. In this case it's a length, so I'm going to take the positive, so this is positive 10. Alright, the other bit of math we need to review is SOHCAHTOA. SOHCAHTOA is just a way to remember your trig ratios. If you have a right angle triangle, so just like Pythagoras' theorem, you need a right angle triangle for SOHCAHTOA to work. You're trying to find the size of an angle, so either this angle or this angle, obviously you know that one's 90 degrees, so you're trying to find this angle. Then the side that's furthest away from the angle you're interested in, that's called the opposite side. The side close to you that's also close to the right angle, that's the adjacent side. And the side that is close to you but opposite the right angle, that's the longest side, that's the hypotenuse. Knowing that, so opposite, adjacent, hypotenuse, you can set up these trig ratios. So sine of your angle, theta, is equal to O over H, so that's opposite over hypotenuse. The ca bit is that cos of your angle, so C for cos, is A for adjacent over H for hypotenuse. So adjacent over hypotenuse. And the TOA part is that tan of your angle is opposite over adjacent. Alright, how do we use these? Let's say in this triangle here, I'm trying to find that angle there. I look at which numbers do I know, which sides do I know. I know the opposite and I know the adjacent side. So that means I'm going to want to use TOA because it has opposite and adjacent in it. I can't use sine or cos because I don't know the hypotenuse, so I'm not going to worry about those. Just use the TOA part. So tan of my angle is going to be that opposite side, which is the 6, divided by the adjacent side, which is the 8. Alright, I can calculate that. 6 divided by 8, that's going to be 0.75. But how do I get the theta out, right? Theta is inside a tan function. So to get that theta out of your tan function, we're going to need an inverse tan. So that's tan to the minus 1 of the value over here, the 0.75. So on my calculator, I do a shift tan, gives me tan to the minus 1 of the 0.75, and my calculator is in units of degrees, which is where you want to be for most things in physics. I get a theta of, I've got 2 sig figs, so I'll write it down as 37 degrees. And I'm done. We can use our trig ratios to do more than find angles though, actually. If we know an angle in a right angle triangle, you can use your trig ratios to find the lengths of sides. So say this right angle triangle right here. So right angle, I know the angle 30 degrees, and then I'm looking for the adjacent side and I know the hypotenuse. So if I'm looking for adjacent and I know hypotenuse, sounds like I'm going to use the cos trig ratio, the ca. So cos of 30 is going to equal my adjacent side, that's A, divided by the hypotenuse, which is the 12. All I have to do to rearrange this for A is multiply both sides by 12. That's going to get rid of my 12 on the bottom here. And I'm left with A is equal to 12 times cos of 30 degrees, which is, so 12 times cos of 30 is 10, and I'll just stop there because I only have 2 sig figs in my angle, so I can't write any more sig figs down. So that's side A. All right, this one, same idea. In this case, I want to know the opposite side, and I know the hypotenuse, and I know an angle. So it sounds like I should probably use the sine trig ratio because I want opposite, I know hypotenuse. So I'll write down that sine of my angle 30 degrees is that opposite side, which is B, divided by 12. Same way we need to rearrange as before, multiply both sides by 12. That gets rid of the 12 on the bottom here and isolates for side B, which is going to be 12 times sine of 30 degrees. Sine of 30 degrees is a half, so 12 times a half is going to be 6. So B will equal 6, and I'll get to write 6.0 because I have 2 sig figs there. And I'm done. All right, the next little bit of math is not so much math review, but maybe math looking ahead. When you get to calculus and vectors, you're going to be doing tons and tons of stuff with vectors. We'll just introduce them very briefly in this course. First, what are they? So there's 2 sort of ways a variable could be. It could either be a scalar, which is just a number, it's just a magnitude, just has sort of a quantity, or a vector. And a vector is a number, so it has a magnitude to it, but it also has a direction. So a vector is a number with a direction. If you have a variable, let's say the variable is v, you want to indicate that it's a vector, then what you want to do is show that it has a direction to it. So to do that, we put a little arrow on top of it, and that just tells us this is a variable with a direction. That little arrow just means this guy is a vector. Notice it's not a full arrow. It's because drawing this every time would be annoying. It takes 2 pen strokes, whereas drawing this is a little bit faster. Sometimes we get lazy and we don't always even draw that arrow on top, but the best way to do a vector is like this with a little tiny arrow on top. Let's look at a few common vectors that we're going to run into in our course. All right, so here's a scalar. A scalar is distance. Distance is just the ground that you cover when you take a trip. So its symbol is d, or sometimes delta d, a change in position. The unit of distance is just meters, that's how far you go. The vector version of that is displacement. So displacement is how far you traveled from A to B, not taking into account the path that you wandered on. So it's going to have a direction to it, and we denote that by putting just a little arrow on top of the symbol. So its symbol is actually also delta d. Both distance and displacement have delta d as their symbol, but you can tell them apart because displacement will have that little arrow on top. And the SI unit is of course meters too. It's still just a measurement of how far you've traveled. For speed, we use the symbol S for speed, and its units are meters per second. Velocity is a speed with a direction. So its units are still meters per second. The symbol for velocity is v, and we put the little arrow on top to say, hey, this guy's a vector. All right, some more scalars. Time is a scalar, right? Time doesn't have a direction to it. You don't say 5 seconds north, it's just 5 seconds. Its unit is seconds. Energy, also just a scalar, just a number. You don't have 10 joules forward, you just have 10 joules of energy. So energy has a SI unit of joules, symbol is just capital E. A few more vector examples. Acceleration is a vector, so that has a direction to it. Its symbol is little a. Its units are meters per second squared. Another vector that we'll see in our next unit after this one is force. When you apply a force to something, right, you can apply force north or apply force east, and that's a different force. So it has an arrow on top of it as well. That's a vector. The units of force are newtons. That's just a few of the vectors and scalars we'll see. Let's look a little more closely at distance and displacement. So distance is the scalar, displacement is the vector, and they're actually 2 very different things even though they seem very similar. So we'll kind of look at it in the context of this example. Let's say you start here, and then you walk 5 meters to the east, then 4 meters south, then 2 meters west. If I want to know how much distance you covered, that's literally how much ground you covered in this whole journey. So I'm just going to add up all these little distances that you covered to get your total distance. So my delta D, without an arrow, just my distance, is going to be 5 meters plus 4 meters plus 2 meters. Altogether, I cover 11 meters. And there's no direction to that. That's just how much ground I've covered overall. I walked 11 meters. Displacement is very different. So displacement is how far you've gone and in what direction from start to finish. So displacement is this right here. So that is your displacement here. That's delta D with an arrow, with the vector arrow. So figuring out that takes a little bit more work. So what we need to think about is how far I've come in this direction, how far I've come in this direction, and then I can put those two together using the Pythagorean theorem because it's a right angle triangle. So I'll just redraw it down here. Here's your delta D with a vector arrow. Here's the distance I travel in the east direction. Here's the south direction. The east direction, I travel 5 meters east and then I go back 2 meters west. So overall I went 3 meters east. Right? So this is 3 meters here. In the south direction, I traveled 4 meters south and that's it. So I just put 4 meters here. Then I get to use Pythagoras' theorem to calculate delta D. So delta D squared would be the 3 squared plus 4 squared. So delta D is going to be the square root of 3 squared is 9, 4 squared is 16. That makes 25 under there. The square root of 25 is 5 meters. So your delta D is 5 meters. But we're not actually done yet because I don't just care about how far I've traveled, I care about the direction, right? It matters what direction your displacement is in. So I'm going to need to find this angle here. I have to tell you the direction. I can't just sort of say, oh, it's some funny angle. I have to tell you what that angle actually is. For that, I'm going to need my trig ratios, my SOHCAHTOA. So I know the opposite side from my angle is 4. The adjacent side is 3. So that means I'm going to use tan. Tan of my angle will be 4 over 3. And that means my angle will be the inverse tan of 4/3. Plugging that into my calculator, I get 53 degrees. All right, so that's my angle there. This is my displacement here, and I can kind of put the two together by saying the displacement is 5 meters at 53 degrees. Now how I could describe this is it's 53 degrees to the south of east. So south of east. There we go. And that is my full displacement there. So don't forget you need a direction with your displacement because it's a vector. Okay. Average speed and velocity. So this is sort of our next set of scalars and vectors. So speed is the scalar. So speed, how fast you're going, is actually your distance, which is also a scalar, over your time, how much time it takes you to cover that distance. This one is going to be a scalar quantity here, and it comes from a scalar, so that kind of makes some sense there. The formula for average velocity is v with a little arrow. It's a vector. It's going to be displacement, delta d with the arrow, over time. So velocity will be in the same direction as your displacement. So if my displacement is at some funny angle, velocity is at the same funny angle. And this is average velocity over the whole trip. Let's look at a couple examples here. First, I have a little baby who's moving everywhere right now. So we'll use her as our example. Let's say she crawls 3 meters forward. So she goes like this, 3 meters forward. She picks up a ball, turns around and crawls 7 meters backwards. All right. First I want to know her average speed. So average speed, we said, is distance over time. The distance that she travels is going to be that full distance that she covers through that whole journey. So the delta D on top here is going to be the 3 meters plus the 7 meters, which is 10 meters. The time on the bottom here, we're told, is 5 seconds. So that's always a scalar. Plugging those in, I get my speed here. It's going to be the 10 meters divided by the 5 seconds, which is 2 meters per second. So the baby's speed is 2 meters per second. And there's no direction to worry about there because that's a scalar. Next, we'll find the baby's average velocity. So this one's going to be a vector. So it's the displacement, which is a vector over the time. All right, finding that displacement means starting from where did the baby start, where did the baby end up, and that is the displacement right there. So that is your delta D with the arrow. That's the displacement. She went 3 meters forward, 7 meters back. That means overall she went 4 meters backwards, right? So her displacement is 4 meters backward. The time is still 5 seconds. So we can toss that into our velocity equation. We get the velocity is going to be 4 meters divided by 5 seconds. That gives me a velocity of 0.8, and I get to toss in another 0 there because I have 2 sig figs meters per second. I'm not done. I need to indicate a direction. The direction of my delta D is backwards, so that means the direction of my average velocity will also be backwards. Velocity is in the same direction as your displacement, and that is my average velocity right there. All right. Alright, in this example, you travel 34 kilometers west and then return to travel 20 kilometers east. So let's just draw our little never eat shredded wheat thing here so we know which way is west and east. We start out 34 kilometers due west. Right away, I'm going to put that into meters. We always work in our SI units. After I get there, I turn around and go 20,000 meters due east, or 20 kilometers due east, and that brings me back to here. All right, I know my average speed, so I'll put that over here. Speed is 70 kilometers per hour, and I want to know how long the trip was. That's the time. First thing I need to do is a little unit conversion. So switch the 70 kilometers per hour into SI units, which is meters per second. To do that, I need to get rid of the kilometers. So I put 1 kilometer on the bottom. 1 kilometer is equal to 1,000 meters. So that's going to cancel my kilometers. Next, I need to cancel the hours. So I have hours on the bottom here. So I'm going to need to put 1 hour on top in order to cancel them. 1 hour is equal to 60 minutes. That cancels my hours. I'm not quite there yet. I need meters per second, not meters per minute. So I'm going to I need to get rid of this minutes, which is on the bottom. I put 1 minute on top. A minute is equal to 60 seconds. Seconds on the bottom. Cancel the minutes, and I'm left with the units I want, meters per second. So now all I have to do is calculate that. So I'll do the 70 times the 1,000 over 1 times 1 over 60 times another 1 over 60 right here. And that gives me a speed of 19.444 meters per second. I'm keeping lots of decimals now because I'm going to need this number later and I don't want to make rounding errors. So don't worry about sig figs until your final answers of any problem. All right, we know speed. We also know the distance. So the distance traveled is just going to be this 34,000 meters plus the 20,000 meters, right? It's the total ground covered. So 34,000 plus the 20,000, that'll give us 54,000 meters. I'm trying to find time, so I'm going to start with my speed equation. It's delta D over delta T. This is a really great chance to practice your equation rearranging. I'll use my little triangle thing that we talked about in our video on rearranging equations. So delta T in the bottom here is going to be delta D on top. See how it's kind of over the S, so it's over S like that. All right, next we just get to plug in our numbers. Delta t is going to be that delta d 54,000 meters over the speed 19.444. When I plug that in, 54,000 divided by the 19.444, I get a time of 2,777.14 seconds. I'm keeping tons of decimals right now. That's because I'm going to need this time later on. But because this is a time that I'm asked for as part of the question, I need to also write it down in sig figs. So in sig figs, there are just two significant figures in this problem. I'll have to write it as 2.8 times 10 to the 3 seconds. There's my time. All right, the average velocity. Velocity is your displacement over your time. So what I need to find here is the displacement. When I look up here, I can see my displacement is the how far I go from start to finish. So that's my delta d with the arrow, the vector kind. Displacement then is going to be the 34,000 meters to the west minus the 20,000 meters to the east, or if I want to even think about this a little bit better, I might make the 34,000 the negative because it looks kind of backwards on my page here. We'll talk about coordinate systems soon. And then the 20,000 I might make positive. In any case, what I get is a negative 14,000 meters, or I could say 14,000 meters to the west. The important part is what direction is this delta d in. The time, I already know, I just calculated it, but I'm going to use the non-rounded version, and I just get to plug all that into my velocity equation. So velocity is delta d, that's the 14,000 meters to the west, over the time, that's this guy here, and that gives me, I'm just keeping the numbers in my calculator as I go, that way I don't have to make any rounding errors at all, just a tip there. That gives me a velocity of 5.0 meters per second. I have to write down a direction. Velocity always has a direction because it's a vector. The direction of velocity is the same as the direction of the displacement. The displacement was west. That means my velocity is going to be west as well. And there we have it. Okay, our last example of this average velocity and average speed stuff, we're going to do a SOHCAHTOA one. So if we're walking to class, say we walk 12 meters north and then 5 meters west, this right here is our distance. So our delta d distance is just going to be 12 meters plus the 5 meters, which is 17 meters here. I want to know the average speed. So speed is that distance over time, and I'm actually told that it takes me 20 seconds to get to class, so I know delta t is 20 seconds already. I can just plug my numbers right in and I'm good to go. So delta d is the 17, time is 20 seconds, toss that into your calculator, 17 divided by 20 is 0.85, units are meters per second. And there's no direction on that because it's a speed, so don't forget a unit, but no direction to worry about. Average velocity is going to take a little bit more work. The problem is average velocity is displacement over time, right? And displacement, I have to figure out using Pythagoras' theorem in this case. So displacement is this vector right here. That's my delta d displacement. To calculate delta d, I'm going to need Pythagoras' theorem. So I'll just do that on the side here. So delta d squared would be the 5 squared plus the 12 squared. When I square root both sides, so delta d, square root both sides here, I'm going to have 25 plus 144. It's going to be 169 in there. Square root of that is 13 meters. So delta d is 13 meters. I'm not actually done even finding delta d though, because delta d has a direction on it. And to state the direction, I can't just say up at some kind of angle somewhere in between north and west. I have to actually give what that angle is. To To find that angle, I'll need a trig ratio. I'm going to use the tan ratio. It's a nice one because I know the opposite, which is 5, and I know the adjacent, which is 12. And the TOA of SOHCAHTOA tells me that tan is opposite over adjacent, so the 5 over the 12. Solving for theta then, I'll do the inverse tan, so inverse tan of 5 over 12. That gives me 22.619 degrees. I'm going to round that off to just 23 degrees because I have two sig figs. Okay, and that's 23 degrees. If I want to describe it a little bit better, it's 23 degrees to the west of north. So west of north. Now I know delta D. Now I can use that to get my average velocity. Average velocity is delta D over delta T. Delta D is 13. The time is 20 seconds still. That doesn't change. So I do the 13 divided by 20. That gives me a velocity of 0.65 meters per second. And then the angle, or the direction of the velocity, is going to be the same as the angle for the displacement. Velocity points in the same direction as displacement. So 23 degrees west of north. And I have my velocity there. All right, let's take a look at coordinate systems next. So we kind of alluded to this briefly, but these are really, really helpful. And we're going to use these all the way through this unit and the next unit. Very handy for dealing with vectors. When you're moving in just the x direction, so you're just moving horizontally, forwards or backwards, it's very helpful to indicate which direction is positive and which direction is negative. We're going to do this for pretty much every problem we do. We start with this. I'll say that positive x is this way. That means that anybody moving this way is going to be negative x. You don't have to write that on this side because it's kind of indicated by the fact that you said positive x is this way. You're actually allowed to set positive x any direction you want. So if for some reason you wanted to make positive x backwards, you can do that. You just have to make sure that every time something's moving backwards, it fits with that convention, and every time something's moving forwards, in that case it would be negative. So I usually just make positive x forwards and then I just go with that every time. It just makes it a little bit simpler. But you can actually set positive to be in any direction you want. We're going to make it forwards most of the time. So if we make positive x forwards, then that means that forward motion will be positive. So that'll be positive velocities. And as I move more forward, my displacement will also become positive. Backwards motion will be negative velocities. So my average velocity will be negative if I'm overall moving backwards, and stopped is of course 0 velocity. If I'm not going anywhere, then I don't have any velocity at all. The same thing works vertically, exactly the same idea, so just set up your y coordinate system is what we use for the vertical direction, just like on a graph. Make y positive in the up direction. That means anything moving down is negative. Anybody moving up, that's a positive velocity. So upward motion is going to be positive velocities. Moving down will be negative velocities. And stopped, of course, is still 0. All right, we can put these two together. We can be moving both horizontally and vertically, right? If you're moving at an angle or doing some sort of cool parabola, we're going to do lots of problems like that. So that's two-dimensional motion. We're not going to get to three-dimensional motion in this course, but you definitely will if you continue with physics. It's quite fun. So for a 2D vector, it's going to have an x and a y component. So here's velocity. It's at 3 meters per second at some angle, 25 degrees, kind of angled above the horizontal here. That vector is going to have an x component. That's like the shadow of my vector along the x-axis, along the ground. So it's got to line up with the point here. It's got to be in the direction of the actual vector. So if this guy's overall kind of going forward, then the x component needs to be going forward. It needs to have an arrow pointing forward on it. I'm going to call it Vx here. That's the x component of this velocity. The y component, notice how overall this vector is pointing up. the y component then will be going up. So it needs an arrow on it too. It's pointed up. I often draw components as dashed lines. You can do them like in a paler color or something, that's fine too. So this is Vy, it's also an upwards vector here. And has to be perpendicular, like straight up and down to be in the y direction. In this case, both Vx and Vy are positive, right? Because I'm moving forward and I'm moving up. If I was moving backward, then Vx would be negative. Okay, let's look at a few more and we'll just calculate some of these things. So this is a velocity kind of in the up forwards direction, and in this case I'm told this angle in here. So I'm going to find the y component, has to go just to the tip of the vector, so be careful how you draw it. That's Vy, and then Vx. Notice how this guy's moving overall forward, so Vx has to have a forwards arrow on it. Let's solve for Vx first. I could use my SOHCAHTOA to get this, right? I'll just write out SOHCAHTOA over here. I know the hypotenuse, and I know this angle here. I want Vx, which is the opposite, so it looks like I should use sine for that, right? Sine of that 75 degrees is going to be my opposite, which is Vx, divided by the hypotenuse, which is the 7 meters per second here. Rearranging that for Vx, I just need to multiply both sides by 7. So I'll get Vx is 7 times sine of 75 degrees. And that is sine of 75 times 7 is 6.76, and the units, it's a velocity, will be meters per second here. Vy, so that's this component of the velocity right here. So that's actually the adjacent side, and I know the hypotenuse. It's good to go back to what you know from the original picture. You don't have to use Vx, so we won't bother. That looks like I should use the ka part of SOHCAHTOA. So cos of my 75 degrees is going to be equal to the adjacent, that's Vy, divided by the hypotenuse, that's my 7. Multiply both sides by 7. Vy is 7 times cos of 75 degrees. Toss that into your calculator. Cos of 75 times 7. I get Vy is 1.81 meters per second. Alright, kind of got the hang of it. We'll do a few more just to make sure you're feeling good with this. Here's one that's going sort of down and forwards. So Vx is going to be positive here because it's forwards. So that has a forwards arrow that's in the positive x direction. But Vy, notice that this vector is overall going down. So Vy we have to make negative when we get to that. Start with Vx. Vx is this one. Vy is this one. So Vx is the adjacent side, and I know the hypotenuse, so I should probably use the cos identity. So cos of my 30 degrees is going to be the adjacent, which is Vx, divided by the hypotenuse, which is the 5. Rearrange that for Vx. I get 5 cos 30, which is going to be cos of 30 times 5, 4.3 meters per second. For Vy, using my trig ratios here is just going to give me a value for Vy, but it doesn't give me the sign. Positive or negative sign comes from our picture. So we look at the fact that Vy is down, and that tells us that it's negative. It's not going to just sort of pop out negative from our math. So we have to pay attention to what's actually going on. So I need the opposite here. I have the hypotenuse. That sounds like I should use sine. So sine of 30 is going to be that opposite side, the Vy, over the hypotenuse, the 5.0. Vy, multiply both sides by 5. It's 5 times sine of 30. Sine of 30 is just a half, so that's going to be 2.5. But wait, it's down, so I need to put a negative sign here. So watch out for that. Use your picture, use your coordinate system to know which things are negative or positive. If it's overall down, our coordinate system is typically with y is positive up. That means we're going to need a negative sign there for your Vy. All right, and don't forget the units too, meters per second, because these are all velocities. Alrighties. Here's one that's actually a lot easier. So here I just have a vector straight down. So what is the x component of this vector? Well, there's actually no part of it is pulling you in x at all. If it's straight down, the x component is 0. All of this vector is in y. Looking at it, notice that it's down. So this is the case where you have to watch out. Vy is down. Our coordinate system is y is positive up, so y is negative down. That means Vy must be negative 4 meters per second. That negative is the one telling you that it's down. Do one more. A vector that's just horizontal. In this case, all of the vector is in x, so Vy will be 0, and Vx is going to be the full 4 meters per second. In this case, it's forwards. X is positive in the forward direction, so that's going to be a positive value. Sometimes what we're looking for is the total velocity, and we find it using the components. So this is sort of going the opposite direction. For this, you'll have a situation where you know Vy, you know Vx, you're trying to find total velocity, and that includes, of course, the angle because the velocity has a direction. So if we want to find V, your best bet is going to be to use the Pythagorean theorem. You've got a right angle triangle here, so the Pythagorean theorem is that V squared is going to be each of these components squared, so 2.1 squared plus the 3.4 squared, square root both sides. You get velocity on its own is going to be the 2.1 squared plus 3.4 squared. Tossing that into my calculator, 2.1 squared plus the 3.4 squared, square root the whole thing. I get 3.99. I have 2 sig figs, so I need to round that off to just 4.0 meters per second. Velocity has a direction, so I need to indicate that using the angle. Best to go back to your picture, see what you know. You know the opposite side, and you know the adjacent side. So it seems to make a lot of sense to use the TOA part of SOHCAHTOA, opposite over adjacent. Of course, you could use sine or cos using your hypotenuse now that you know it, but it's just better to go back to what you knew at the beginning if you can. So tan of your angle theta is going to be that opposite side. Opposite my angle is the 3.4 divided by the adjacent side. Adjacent to my angle is the 2.1, so 2.1. I'm going to get theta by inverse tanning that, so I'll do the inverse tan of, in brackets, 3.4 over 2.1, and that gives me 58 degrees. And that is my velocity with its direction. Let's do just one more example. This is one where you have a negative component, so Vy is down, so it's negative. When you're finding total velocity, you actually don't need to use that negative sign. You can definitely see why with your calculation of V. When I do my V squared is 3.5 squared plus the negative 2 squared. Of course, if I square a negative, I just get a positive anyway, so that negative sign isn't influencing anything at all. V on its own, it's going to be the square root of 3.5 squared plus 2 squared. You can do negative 2 squared, but it makes no difference at all. So just do 2 squared, square root that whole thing to get your velocity. My velocity is 4.03. I have 3 sig figs here, so 4.03 meters per second. Every velocity has an angle, so I need to find that angle theta in there. My angle is going to be the opposite over the adjacent, and again, don't worry about putting that negative sign in. The negative sign will make no difference for your calculation of V. It actually will make a difference for your calculation of theta, but it'll just give you a negative angle if you put it in, and that might confuse you. Essentially what you need to calculate that angle is the length of that side. Even though it is negative, it is down, you just need the length or the magnitude of it, which is the positive value. So it's okay when you're calculating theta to use the positive value. So tan of theta is going to be the opposite over the adjacent. So I'm here, my opposite side is this one, so opposite divided by the adjacent, 3.5. Okay, so it'll be the 2 over the 3.5. I need to use my inverse tan, so I'm going to do inverse tan of 2 over 3.5. That gives me 29.7 degrees. All right. The last thing we're going to do in this video is looking at how do we add a whole bunch of vectors together. Let's say we want to find a total displacement and there's all these little displacement vectors that I need to put together to get that total displacement. Your best strategy is going to be to split every vector into its components. So put every vector into its x and y components, and you're just going to use your SOHCAHTOA for that. Next, you're going to take all the x components and add them up. So you're going to make sort of a column of x stuff and add up all the x components. Make a column of y stuff, add up all the y components. What you're going to get is a net x, a sum of all your x things, and a net y, a sum of all the y things. That little sigma symbol, capital sigma, means sum of. It means just add up all your x and y. Your last step then is just to put those two things together. So you'll have some x stuff, that's your sum of all your x stuff. Then you'll have your y stuff, all the y stuff that's been added together, and that in a triangle will give you your overall total displacement. So we add up all our x stuff, add up all our y stuff, put them together in a little triangle. Our total displacement, don't forget, it will have an angle, so we'll have to calculate that too. All right, I'll show you what that looks like in an example. Here it is. Sorry. All right, so you've got a duckling is waddling along this route. So she goes this way, then goes this way, then goes back that way. What we care about is our overall displacement right there. That's what I want to know. Delta D, overall total displacement. But there's all these little pieces. So if you tried to use just geometry to solve this, you would have a horrible shape, right, that you're dealing with. It would be super, super messy geometry. Using this sort of components method, we find it works out quite simply. So I'll start with my D1 here. D1 has two components. It has an x component here. This is my D1x, and a y component. There's D1y. Next I've got my D2. Has an x component, D2x. Notice how it's forwards, right? This vector is pointing forward, so it has an arrow on it, it's forwards. And a y component, it's up. Don't forget those arrows on your components here. They're so important because they tell you the sign. So I know D2x is going to be positive because it's forwards, whereas like D3x is going to be negative. It's a backwards one, right? Okay, and that's my D3x has no components. It's all just in the x, so I'll just draw it again, but it's all in the x direction. Okay, so I said we were going to make a chart of x and y stuff, so let's do that over here. So here's everything about x and everything about y here. All right, let's start with D1. I've made that one blue here. I'm going to look for D1x and D1y. I'm going to just show you a quick trick here. You can do your whole SOHCAHTOA, go through the whole SOHCAHTOA thing. Say, okay, I've got like, I need cos because I'm like adjacent and hypotenuse. You can do all that. But there's actually a nice trick because you're going to do this so often where you have a hypotenuse and you need adjacent or the opposite side. Basically you need the components, dx and dy. So because you're going to be doing this like 50 times a day, I'll just show you a quick trick to speed you up. And that is sort of the mnemonic that cos is close. So if you're doing the side that is close, you're just going to take the hypotenuse, cos your angle. So hypotenuse multiplied by cos of your angle. Sines, if you see a sine on the highway, it's very far away. So if you've got the side that's far away from your angle, sine is far away. You'll have the hypotenuse multiplied by sine of the angle. So feel free to check my work using SOHCAHTOA, but I'm going to use that quick trick here. So D1x is close to my angle, cos is close, so 7.1 cos of 35 degrees. And let's calculate what that is. When we're calculating these, I'm going to keep lots of decimals just to make sure I don't make rounding errors later on. So that one works out to 5.816 meters. Let's do D1y. It's far away from my angle, sine is far away. So it'll be 7.1 sine of the 35 degrees. So I'll do 7.1 sine of 35. That gives me 4.8 5.072 meters. All right, then let's go on to our D2. D2 has an x component, which is close to my angle, right? So cos is close, so that's going to be a cos. So D2x will be 5.4 cos of 55 degrees. By the way, do you remember cos is close? Don't remember cos is always x-axis. Depending on where your angle is, you might have cos is y-axis, right? If I'd given you this angle up here, then the d2y would be cos, right? So just remember cos is close. Don't think cos is always x. It's not always x. All right, let's calculate that one. So 5.4 times cos of 55 is 3.097 meters. And then I have my d2y. That's this one over here. It's far away from my angle. Signs are far away on the highway, so it's going to be 5.4 sine of 55 degrees. Plugging that in, 5.4 times sine of 55. And I get 4.423 meters. My very last one is D3. Now D3 is really nice. It's all in x. So I could just write down D3x is all of that 6.7 meters, but that is wrong. Very important to always check my coordinate system. My coordinate system says x is positive, and D3 is completely backwards here, so this has to be a negative value. It's really important, or the whole number at the end will be wrong. D3y is an easy one. There's no component of D3 that's pushing you up or down, so the y component is 0. All right. So that's all my x stuff and all my y stuff. My next job is to find the sum of everything in x and the sum of everything in y. So that sigma, right, means sum. So I'm going to add up all these values. That's why that sign is really important here. And I'll add up all of these values to get sum of things in y. Okay, starting with x, I have the 5.816, I have the 3.097, and I have the negative 6.7. So the sum of all my x stuff is 2.213 meters. The y side, I have, just slide this over, 4.072, and I have the 4.423, and then I have plus 0. All that adds up to 8.495 meters. Okay, so I've added up all my x stuff, I've added up all my y stuff. My last move is to squish x and y together to get my overall delta D. This guy, that's what I'm looking for, right? So I need to put my overall x, my overall y. So I always draw this as just a little triangle on the side. I'll have my x here and y stuff here. So x, the sum of the x stuff, is 2.213 meters, and the sum of the y stuff here is 8.495 meters. I'm looking for the overall delta D, this value right there. That's going to be Pythagorean theorem. So delta D is going to be the square root of the 2.213 squared plus my 8.495 squared. I'm running out of room. All right, so 8.495 squared plus my 2.213 squared, square root that, and I get my delta D. Now I'll just check sig figs. I've got 2 sig figs everywhere, so my delta D is going to round to just 8.8 meters. I'm actually not done. Delta D has an angle to it, right? So I need to find that angle theta. This is a good one here. It actually doesn't matter if you wanted to find that one, that's okay. This is just maybe the more normal one down at the base of the vector. So theta, I'm going to use a tan function for that. Tan of theta will be the opposite, that's this value, over the adjacent. So the opposite is the 8.495 divided by the adjacent side, which is the 2.213. Toss that into my calculator. I'm going to be doing an inverse tan to undo that tan function and get theta out, of 8.495 divided by 2.213, and that gives me 75 degrees. So theta is 75 degrees. And there's delta D, there's theta, and we are done.